All right, guys, we're looking at section 7.3 today. Today and one more section, and then we're done with chapter 7, and we're done with the sections we're going to cover in college algebra. So we're going to be dealing with matrices today as a way to solve systems of equations using inverse matrices. We're going to do some stuff by hand, some stuff on the calculator. Ultimately, in the homework, they're going to ask you to do a little bit of both, but make sure you're really comfortable with the calculator part, because that will make things a lot simpler for you. Okay, so for the first example here, it says if I multiply these two matrices together, I'm supposed to get this 2 by 2 on the right. They want me to find A, B, C, and D. In the end, I'm going to end up with some systems of equations here. If you remember the multiplication, if I want to get that result that's in row 1, column 1, I need to take row 1 times column 1. So let's do that. A times 1 is A, 4 times C is 4C, and that's going to have to be that 1 that's in the upper left. If I want to get to, if I take row 1 times column 2, so row 1, column 2, that would be the 4, so row 1 times column 2, that's going to be B plus 4D equals 4. Okay. Now if I take row 2 times column 1, that's this location, so negative 2A plus 3C, and that's going to equal negative 2. And row 2 times column 2 is negative 2B plus 3D, and that's supposed to equal that 3. Okay, so now I just have a couple of systems, and you'll notice how I set it up. So I've got the A's in the same column, the C's in the same column, etc. That'll make your life a little bit easier. Using elimination, I think if we multiply everything in this first row by 2, then I'll get the A's to be the same and the B's to be the same, and I can eliminate those. So when I multiply this row, I get 2A plus 8C equals 2. Leave the second equation alone. Okay. Similarly over here, multiply the first row by 2. Second row we're going to leave alone. Okay. And now when I add these together, I should eliminate that first column. So the A's are gone here. I have 11C equals 0. So that tells me that C is 0. Okay, and if C is 0, if I go back to one of these first equations, this would become 0 and A would be 1. Okay, over in the second system, add up the first column and I get 0 for the B's. I get 11D equals 11. So that means D is going to be 1. Okay, and if D is 1, 4 times 1 is 4, subtract 4, B has to be 0. And so now I've got all 4 spots figured out. Okay, so there's going to be a little bit of that. We did some multiplying of matrices in a previous section, so you should be okay with this. Okay, example 1b, given A and B, determine if A times B is A and B times A is A. Easiest way to do this is on the calculator, you guys. So if you remember, if you hit alpha zoom, it gives you the dimensions, and you can go ahead and then just plug them in. So I went alpha zoom, I created a 2 by 2, I put that matrix in, and then times, I did alpha zoom again, put that matrix in, and multiplied them. Sure enough, that's matrix A. And when I did them in the opposite order, remember multiplication of matrices is not commutative, so it's not always the same thing. In this case it is though, because you're multiplying by the identity matrix, and if you multiply by an identity you get back what you started with. So use your calculator to just determine that kind of stuff. Okay, example 2a is more of what we did previously. So we're going to multiply these together to get the identity matrix. Well, the only way to multiply two things to get to the identity is to multiply by the inverse. So in essence, when I find A, B, C, and D here, I'm finding the inverse. So this is one way of finding the inverse. There's going to be multiple ways that we do it today. This is one though. So similar to what we did before here, you guys. So 6A plus 5C, row 1, column 1, that's supposed to equal 1, okay? Then if I do it to the second column, 6B plus 5D, that's going to equal 0. Now if I take row 2 times column 1, that's 2a plus 2c equals 0. Over here, row 2 times column 2, that's 2b plus 2d equals 1. So again, I'm trying to solve this system of equations. I think if I multiply this second row this time by -3, I'm going to get this -6a and get those to be equivalent. So I'm going to leave the first row alone this time. But I'm going to multiply the second row by -3. So -6a minus 6c equals 0. Over here, leave the first row alone. Multiply the second row by -3. -6b minus 6d equals -3. Okay? Add the systems together and I should lose the first column. So here, the a's are gone. This gives me -c equals 1. So I know c's got to be -1. Okay? And if c is -1, so 5 times -1 would be -5. I add a 5 and I get 6 divided by 6. A would be +1. Okay? In the second system, if I add these up, the b's are gone. I get -d equals -3. That means d is going to be 3. Okay? Knowing that d is 3, if I put this in here, 5 times 3 is 15. Subtract 15, you get -15 on the other side. And then divide by 6. -15 divided by 6 is -2.5 if you throw that into the calculator. So if you then put that back into the matrix, that new matrix there is the inverse of the first one. So when you multiply them together, you get that identity matrix. Okay? 2b, use the augmented matrix method to find A inverse. Okay, this one's a little bit trickier, you guys. A little bit more of a pain. We're not going to do this very much, but I will show you so that you can kind of see what's going on. So you've got 6, 5, 2, 2, and we want it to be that augmented matrix. So you want it to be that identity matrix over here. So what we end up doing is recreating this so that it is the identity matrix, and then this will become the inverse. So I have to rearrange. I'm going to start by taking row 1 and row 2 and interchanging them. Okay? So just going to switch row 1 and row 2 around so that I get a 2 in the upper left-hand corner. Okay? I want to get a 1 here eventually. I'm not going to do that yet because if I multiply it by half, I get fractions, and I don't want to deal with fractions if I don't have to. But I can make this a 0 pretty easily if I take -3 times row 1 and I add it to row 2. Okay? So I'm going to leave row 1 alone. -6 plus 6 is 0. -6 plus 5 is -1. Okay? 0 plus 1 is 1. And -3 plus 0 is -3. Now I'm there. Okay? Then I would like to have this be a 1, so I'm going to just take -1 times row 2. So I'm not going to change row 1. But I'm going to multiply the second row by a negative, so that's going to, I think that was a -3, so that's going to become a 3, like so. Okay, so I've got a 0 and a 1 here, which is what I want. Okay, I want to make this a 0, so I'm going to take -2 times row 2, so if I make this a -2 and I add it to row 1, that will create a 0 in this spot. So 0 plus 2 is still a 2. -2 plus 2 is a 0. 2 plus 0 is a 2. -6 plus 1 is -5. Okay? And then I'm going to leave the second row the same. Okay? Now I'm really, really close because I've got the zeros here and the 1 here. I'm going to multiply the first row by 1/2 to get a 1 out in front. and then I should be where I want to be. Oh, pardon me. Okay, so half of 2 is 1, half of 0 is still 0, half of 2 is 1, half of negative 5 is negative 2.5, and then 0, 1, negative 1, negative 3. And if you recall from the previous slide, this is what I got for A, B, C, and D. I got the same result. We just went about it using matrices and row operations instead. We're not going to do this very much, you guys, okay? So you might see a little bit of it, but not a whole lot of it. So take down one good example, and you should have good reference for what you need to do in the future, okay? All right. The inverse of a 2 by 2 matrix, here's another way to do this, okay? So if you take 1 over AD minus BC, AD minus BC, which is ultimately the determinant of that, and we're going to take a look at that here in a little bit, times, and then inside the matrix, so this will be a number out front. Inside the matrix, you'll notice that we switch D and A around, and then we make B and C the opposite of what they were, okay? And that's pretty much it. So that's one way of finding an inverse matrix, okay? This is basically saying in an inverse matrix, if you multiply a matrix times its inverse, you get that identity matrix back, and we've already seen that just a little bit, okay? So how about here? Use a calculator and a matrix equation to solve the system. Okay, so the matrix equation here, you guys, is basically this. Okay, you've got the coefficients 1, 4, negative 1, 2, 5, negative 3, 8, 1, negative 2, times some x, y, z is supposed to be these constants over here, 10, 7, 11. So that's the matrix equation that we're trying to solve here, you guys. And if you just think of algebra in general, I need to get rid of this matrix because I want the variables by themselves. Well, the only way to get rid of a matrix is to multiply by the inverse. And if you look over here on my calculator, I took this coefficient matrix, I took the inverse of it, which is just that x to the negative 1 button on your calculator, times this one, because I have to do it, I have to take the inverse to both sides of the equal sign. When I do that, I'm left with 2, 3, 4, which simply means x is 2, y is 3, z is 4. And so that's a really slick way to find the solution to a system of 3 equations, 3 unknowns, 4 equations, 4 unknowns. As long as you have a square system like that, it goes pretty easy, okay? So that's a nice way of solving a system. The determinant of a 2 by 2, I said we're going to talk about this in a little bit. It helps us do a couple things. One, if the determinant is 0, then the inverse of that matrix does not exist. It's called a singular matrix. Because if you recall, at the beginning, a couple slides ago, we had to go 1 over the determinant to determine that number out in front. Well, 1 over 0 doesn't work. So when you find the determinant here, the actual algorithm is to multiply the diagonals and subtract. So A times D minus B times C. That's really all you need to do there. And we'll practice this just a little bit. The only way it works is if it's a square matrix as well. So keep that in mind. Okay, so for this one, 3 times negative 6 minus 2 times 1, negative 18 minus 2, the determinant is negative 20. This matrix here is a 2 by 3. It's not square, so there is no determinant for that one. This matrix over here, 4 times 5 is 20, minus negative 10 times negative 2 is also 20. That has a determinant of 0, which means matrix D does not have an inverse, okay? This one will, matrix D over there does not, okay? Singular matrices are matrices that don't have a determinant, so, or don't have an inverse. So if the determinant's 0, it's a singular matrix. Okay, this is a method of finding the determinant of a 3 by 3. We call it the expansion of minors, okay? And it simply means you're going to pick a row or a column. I tend to pick the first row. If we had more time to discuss this, I would go through kind of how to determine which row. We're just going to stick with the first row to make it easy for you here. Okay, so pick the first row. Then you take that number in the first spot, A sub 1, 1. You cover up the first column in the first row, and those 4 that are left, you're going to find the determinant of those. minus, because for that first row there's a minus in the middle, a sub 1, 2, and then if you cover up that column and row, you're left with 2, 1, 2, 3, 3, 1, and 3, 3, etc. Okay? So you guys can copy that down and study it. I will go through an example with you, though, to make sure that you understand what we're doing here. So compute the determinant. We're going to pick the first row. Okay? There's a 2 in the first row, times what determinant? If you cover up that column in that row, you're left with negative 1, 0, 1, 4. We said with that first row, there's always a minus in the middle. There's a 1 in the second spot. Okay? And if you cover up that column in that row, you're left with a 1 and a 0, and a negative 2 and a 4. Plus, there's a negative 3 in that last spot. Cover up that column in that row, you're left with 1, negative 1, negative 2, 1. Okay? Now I just need to do some of that calculation. So the determinant here, remember, we take a times d minus b times c, so that's negative 4 minus 0, negative 4. Okay? Minus 1, this is 4 minus 0. Okay? Plus a negative 3 or minus a 3. And this is 1 minus 2, which is negative 1. Okay, so I get negative 8 minus 4 plus 3, which is negative 9. Negative 9 is the determinant of that 3 by 3. And we can do this on the calculator as well, and I'm going to show you that down the road here too. But that's how I would do it by hand. Okay? The next one we're going to just say, hey, let's do it on the calculator. So if you go into your matrix menu, okay, which your matrix menu is above that x to the negative 1 button, so you hit second x to the negative 1, you go over to the math column. And in the math column, the first option is DET for determinant, okay? So you choose DET, it gives you a parenthesis. You hit alpha zoom, create a 3 by 3 matrix, you put those numbers in, and you press enter, and it says, hey, your determinant's negative 4, done, okay? And so I have no problem if you guys do that on the calculator, all right? Given the system shown here, 1, form the matrix equation, okay? So that's that 2, 1, negative 3, 1, negative 1, 0, negative 2, 1, 4, times x, y, z equals the constants on the right side. So we've seen that already. We're going to do that to compute the determinant of the coefficient matrix and determine if you can proceed. Again, if the determinant is 0, you can't proceed, but the determinant here may or may not be 0. And if so, solve the system using a matrix equation. So here's what I did. Here's the matrix equation. These are the coefficients. Again, you notice there's a placeholder there because there wasn't a z term in that second equation. So this is the coefficients for x, y, and z in the first equation, second equation, and third equation, times your x, y, z, and then on the right side are the coefficients. Okay? So that's the matrix equation. The next thing you might want to do is find the determinant of that matrix. That's the coefficient matrix. Because if it's 0, I can't proceed. So I go over here, just like I did on the previous slide, and I find the determinant. I get negative 9. Okay? Well, it's not 0, so I can proceed. And then in the calculator, this is how I solve this. In order to get rid of this matrix, I have to take the inverse of it. So I put that matrix in the calculator, alpha zoom, 3 by 3, enter the data. And then I choose that x to the negative 1 button, inverse, times that 3 by 1 on the right side. I press enter. This to me means x equals 3, y equals 2, z equals negative 1. As simple as that, you guys. Okay, what about a word problem? How are we going to tackle this? This looks super complicated, but it's actually, with the use of a calculator, it's not terrible. So a local theater sells 4 sizes of soft drink. 32 ounce, 24 ounce, 16 ounce, and a 12 ounce at the different prices you see there. As part of the free guest pass promotion, the manager asks employees to try and determine the number of each size sold, given the following. Total revenue was $1439.60. There were 9,096 ounces sold, 394 soft drinks sold, and the number of 24 ounce and 12 ounce soft drinks sold was 12 more than the number of 32 and 16 sold. Okay, so if we're going to solve this, we have to write the system first. Okay, so we've got 4 variables we have to worry about here. So it's going to be 4 equations, 4 unknowns. So let's talk about maybe extra large, large, medium, and small for our variables. And we know that our revenue is going to come from these. So 4.5 times extra large plus 3.8 times large plus 3 times medium plus 2.4 times small is going to be this revenue of 1439.60. Okay? And then the ounces, 32x plus 24L plus 16M plus 12S has to be a total of 9,096 ounces. Okay? And X plus L plus M plus S also has to be 394 because we sold 394 ounces, etc., or soft drinks. And so we're going to be able to set up a system relatively easily here. Okay? And that's what's going on over here. So our system ultimately of equations looks like this, you guys. Okay, and then X plus L. Okay, now this last one was a little bit tricky. It said that the number of 24 ounce, but actually I think it said that the number of 32 ounce and the number of 16 ounce was 12 more than the other two. So you ended up with something like this. Okay, so that's the original system of equations that I set up. Well, I need 4 equations, 4 unknowns. So the first one, my coefficient matrix is going to be 4.5, 3.8, 3, and 2.4. The second row, 32, 24, 16, and 12. The third row, 1, 1, 1, 1. Okay, now the fourth row, I need to get these the variables on the right side over to the left side, so I need to subtract the x and I need to subtract the m, and I need to put them in the right column. And we have to remember that this was x, this was L, this was m, and this was s ultimately. Okay, so that x comes over as a -1, the L was positive, the m comes over as a -1, and the s was already positive. Okay, times some variable matrix, x, L, m, and s, equals these constants on the right side, and that 12 will be left alone, and that's where we get that. Okay, so that's the equation. Now if I want to solve it, I take this inverse times this one. So I do that, and I'm left with 112, 151, 79, and 52. Well, let's interpret that a little bit. This means we must have sold 112 extra large, 151 large, 79 medium, and 52 small soft drinks in order to get what we're looking at. Okay, so using inverse matrices, a little bit of stuff by hand, a little bit of stuff on the calculator. Hopefully between the two, you guys will have success. Okay, there's your assignment, 6 to 57, multiples of 3, so 6, 9, 12, etc. So again, questions, pop into the office hours and ask, or email me. Thanks.